What today is like imitation learning. I'm trying to cover is a very basic and like different part of the imitation learning. And I will try to go to the very surface. I won't be able to go to the very deep for this topic now. So first I want to introduce like why like what is imitation learning. So imitation learning came from the concept that imitating some person, what generally like in different domain we always like make decisions. If we collect them the data of the decisions and directly try to uh, transfer them to the machine, that is a kind of like imitation learning, so transferring the skill with every doctors every day see patients make decisions based on some parameters or like uh, driver's drive everything. So this kind of decision transferring to the like a machine, like a driving car or autonomous driving car, try to see the patterns how a drivers drive and try to mimic that. So these are the kind of thing like imitation learn tries to transfer, and generally it has application mostly in like robotics, autonomous driving, and also recently like dynamic treatment regimes also trying to imitate use this. So question is like when generally people use imitation learning. Generally like you have a lot of offline data, like a large amount of offline data, like clinical decisions or thing, and you have like some constraints, you can't directly make a like train a model like a supervised model, a learner model, because like you have to be aware of some constraint, and you can't give any kind of medication to any patient. There should be some constraint, so trial and error is unsafe, such kind of. And also another part is like when you have like very small number of data, like the data set is not very large, and also like there is no explicitly mentioned like why some person did that action, like what is the goal of that action. In such cases imitation learning is used. Also when you try to train a model to be try to make a model more data efficient, the people generally with supervised learning merges imitation learning so that their model becomes slightly more data efficient, and as it tries to be more to the center around the expert. So if I like compare this domain with traditional domain, what I can compare it with. First, I can compare it with reinforcement learning. In reinforcement learning, what happens is you have an environment and some agent which makes some decision and try to learn some policy. Policy is like it says some state of the state of this environment, and it tries to take any decision, tries to make any decision which we call policy. Imitation learning also tries to learn the such kind of policy, and also there is a part of imitation learning inverse reinforcement learning that try to recover reward function, which we will cover later, from the given action. There is no the why doctor making some decision, there should be some reward behind that. So that reward extracting that reward is like inverse reinforcement learning. That is also like similar to reinforcement learning, but imitation learning also similar to like supervised learning. So it's more similar to the structured prediction of supervised learning. Structured prediction means you are predicting not one point, like one decision, just like classification or not, or segmentation. You are trying to make a sequence of decision, like a weekly prediction. So there is a like several decisions you have to make at the same time, or you have to predict like some structure of the sentence. there you are predicting the whole like tree of the sentence. So this is a structure you are trying to predict. So this kind of prediction also like similar like to imitation learning. Let's go like how imitation learning is more similar to reinforcement learning. So we know that reinforcement learning actually try to learn action. What it does, it try different action and receive feedback, and based on that it learn some reward, and by that way it learns a policy. So let's go for real life example. You are trying to learn poker without knowing anything. You just randomly tries different situation. You see your opponents making different decision, and you just tries to like try some action like bet, fold, raise some money, and see, and tries to see like what benefit you like reward you get. So over the time you learn that some situation you find this kind of reward. So that is over the time actually you are learning a policy. So it is like learning through like experience. You make mistake, and with that mistake you learn some policy. Or like and now a robot is trying to learn how to clear a maze. So what it does, like you give a state of the maze, like a different point of the maze. You have environment that represent the whole whole environment of the maze, and it has a table, and this table identifies different location which can be represented as like a different location of the environment. Then each location it tries to make decision. It can go north, east, south, west. Now, every time it tries some action, it gets some reward. Over the time, it knows like if I take this action when I'm here, I will get this reward in future. So over the time, doing this making mistake, it learns that uh, which one is the best action to take when the robot makes some decision. So here it's the kind of a traditional typical example of Q table. You can see like it's like a easier representation, most easiest representation of like a state to reaction reward. Currently, like they have like when you have large state space, you approximate using like deep learning or other state. But if you go to the basic, you can see that the states are like when you're tractable, the states can be like tractable using Q table. Your states can be mapped, state and action can be mapped as a table. Here, each point actually for each state agent sees it like for a position. It throughout the time using Bellman equation learns like what future reward it will get, and after when it reaches the equilibrium, generally the policy doesn't change. Then you have a fixed policy, and that is what the optimal route you got, and the agent learns to solve the maze. Now, how actually a policy now here is being learned in the reinforcement learning. So initially, when you have the table or like a state to action map, generally you have random guesses. When you see the action, you apply the reward using Bellman equation, and you apply like a point, you apply the over the time what could be the discounted reward when you play the game for a long time. And every time you play it, the table changes until it is stabilized. You played enough time. So what happened is like once like you make some decision like for x1, or if you play it is stabilized, you know that from x1 to x in this state you should take the east location, because over the time you've seen that it gives the best reward. So when so every time your table changes or state action map changes, you learn actually new policy. This is the learning of a new policy. You are going from old policy to a new policy every time your table changes until your policy is stabilized. That is we call a stabilized policy. So this happens for everything. If you can track it using a table, you can see that this is how happen here. And for the like the poker example or the maze example, maze is simpler because the number of states possible in the maze is very small. But poker is more complex because it is a partial observable environment. It's like a very large domain. You can't actually track all the like states in a table. Then you have to use some other mechanism like approximation mechanism. So now another part of the imitation learning is similar to supervised learning. If we revisit supervised learning, you can see what we do. We have a model, we have some input feature, and like it is a segmentation, it's learning some segmentation task. What happen is like the model learns to segment the thing, and you have the label, and you calculate the loss and like propagate the loss backward, and like fix the model parameter until you learn the model like something closer to the parameter should be something like that it always generates something closer to the mask, yeah, with a very little error possible. So basically in supervised learning, the model is learning what it has seen. Now generally it is told that the policy is not learned in supervised learning, but I think like in my opinion there is a policy is learned. You can say it as a stationary policy, a policy that is not being changed. So what happening is like your model is learning to make some decision, but based on the data it has seen, and that decision doesn't change any like in future. So like an optimal. And now supervised learning, what happens is it always assume that the training data it has, it's the optimal. It doesn't cover anything outside of the training data. So which we call that out of distribution data. Like when you train a model using some training data, it only sees the data, it trained with it, it learns to make the decision based on the training data. Now, if some sample is very different than the training data, then actually the model like the accuracy of the model or performance of the model like start decreasing. So those kind of data we can say that they are the out of distribution data. Now, if we compare supervised learning policy and reinforcement learning policy, the idea is very simple. Supervised learning policy doesn't change. It learns one policy based on the data it has seen, but reinforcement learning, every time it sees a new action, it changes its policy. Another thing is most of the time reinforcement learning is applied to sequential decision making process, not one step, but supervised learning make decision once. For example, you are classifying something, you show the cat picture. Typically, it is making just once a decision, but reinforcement learning often makes decision is sequence. Like you make one decision, that decision will have impact on the next decision, which will be called like sequential learning. So current decision and affects the next decision unless you are applying an bandit. So current decision and affects the next decision, and next decision will handle the next decision. So if you make decision error in the first decision, your next decision will most likely get some error. So if we now compare imitation learning by versus reinforcement learning, we can see that imitation learning also need to learn a policy based on the data, and it also need to make sequential decision. Like current decision will affect the next decision, and next decision will affect next decision. So and they have to refine their strategy where they will make like a better decision. But problem is dissimilarities are normal typical reinforcement learning has an environment or simulator where they can try any simulation, any amount of simulation until they reaches a like optimal policy. But in case of imitation learning, you have some limited amount of expired data, and you have to copy the policy or learn the optimal policy from that limited amount of expert data. So you don't have any like online feedback such as RL. You have to totally depend on a small amount of historical or the amount of historical data you have. But you have real world constraints. You have to be very efficient. Say about this data. Now, and if we compare imitation learning with supervised learning, imitation learning, as it has some label data, historical data, it's also like supervised learning. It's learned from the like label data, some prediction, making prediction. But also like supervised, if you are making a structured prediction, you are not predicting a whole sequence, a whole like month decision with weekly month decision, or like you are making predicting some like tree or a structure. That's more similar to imitation learning. And also it suffers from distribution shift, which is in terms of supervised learning, there is a thing called domain adaptation, where like you are trained it in one domain, you are trying to adapt it for the next domain, then there is the similar problem happens. But mostly the difference of imitation learning and supervised learning is the like imitation learning needs to policy need to be evolved. So over the time they have to learn new policy that is more accurate, but supervised learning mostly goes into like one policy if you train a like based on one accurate model. And supervised learning, your current decision doesn't affect the next decision, so it is one time decision mostly until like you make some model that has like several steps. One model will affect the output of the input of the another model. Unless that supervised learning, it is not happening it. And obviously supervised learning is assume that the data you have is the optimal, so you can't go outside of the data, and you the accuracy you model is the based on the data, so it's the best accuracy. But in imitation learning, as these models are applied to the directly to the real world, you have to consider that you can't think that data is optimal. You have to change the policy throughout the time until you got something which is approved. So but so imitation learning actually can be learned using supervised learning. Some papers represented that. So imitation learning, the whole learning process of imitation learning considered as a structured prediction, as I mentioned above. And a structured prediction can be converted, like reduced to sequential decisions. Like you have a model, you are making a decision, and you taking the decision and putting it as an input for the next decision. So by that time, like you are making a decision for 7 weeks treatment, you take one decision, you take the decision and input of the second week decision. So this way you make like 7 separate model and make the decision sequentially. So that is how actually supervised learning, imitation learning can be converted to supervised learning. Like weekly plant watering example I gave, like you have to water like 7 weeks of plant watering. So every week you make some decision, you put it the input for the second week. Second week makes some decision, put it in for the, so this may becomes like converted into the sequential decision. Now uh, so we can say like I think kind of discussed this is. So if we go for some major type of imitation learning, generally there are two type of imitation learning I have found till now. One is behavioral cloning, another is inverse reinforcement learning. So behavioral cloning is kind of you have the data and you try to directly clone the data using your model. So what I mean is like behavioral cloning is more you can say like it's more of a supervised learning version. Your version, you say like the data is from some expert and expert is optimal. The decision expert made was optimal. You just have to clone it and you will make the optimal decision. So what happened is like you can directly apply supervised learning. Like you that initial decision and convert it into like a structured prediction or sequential prediction. But problem is like if you have a data set that is very large and cover every possible scenario which is not possible in real life, so basically it suffers from like out of distribution problem. Now another like imitation learning is inverse reinforcement learning, where you have the data, you may have or may not have some model. What you try to do is like you try to say like that their data it has like expert action. Expert made that action because they had some intention. You don't know it why a doctor gave some patient some like medicine, or like why some like robotic like some person who are making like driving, why that person suddenly pulled the brake. Obviously they did it, there is some intention behind it. So you inverse reinforcement learning, what it does, it tries to capture that reward, like intention, using as a reward function. So that is another step. Behavioral cloning is more easier one, and inverse reinforcement learning is more like mathematical and like mathematics driven, and like you have to so map the whole thing into functional space and somehow predict a function how it's like reward function, how some decision is being made. So what you can directly already say the behavior cloning is like the imitation behavioral cloning part of the imitation learning is like can be directly implementing it using like supervised learning. Already like different like models doing that. That is yeah, so there is actually many motives. Some are trajectory based learning and some are more non-trajectory based, but idea is simple. You take the input, put it as a like output, predict it and put to the next iteration. But again, if that data set is not big enough, your model will suffer and it won't make optimal decision for out of the distribution samples. So there are, for this part of behavior cloning, there are some models actually suggested that can try to improve like out of distribution. When you have out of distribution samples, how you handle them. So there are something like confidence based expert curing, dagger or multi-step prediction, or like data as demonstrator. So data as demonstrator is a kind of extension of Draeger. Confidence-based curing is like you have sample a large amount of sample, but you know that all the samples are not optimal. You somehow assign a confidence around each sample, and you just ask the expert when making some decision that I made that decision, is it okay? Expert label it. You every time you have low confidence on some decision, you just collect it based on expert opinion and you retrain it. So when you retrain it, your obviously your model is changed, so your policy is changed. So something like that. So generally you can do it with any like neural net, gmm, anything that gives you some confidence on your every level. And then you ask expert, I have low confidence, this sample is like very lower and like one or twice appeared this type of decision in my data set, I have very lower confidence on it. What I do, expert correct it. If the decision is make, you just enable the update the confidence and retain the next model with that updated data, and like you get a like a better model. So for that, this is one paper actually, it published in EuroPS 2021, which is confidence over imitation learning from the demonstration with varying optimality. this paper is it's similar to what confidence-based curing does. It is covered that. So what they do, these papers, it is directly didn't cover the confidence-based curing. What it does is it's say when we are training some model using for imitation learning with some sample, all demonstration are not optimal. Some are good, some are bad. So we have to automatically, they want to automatically learn those suboptimal or noisy demonstrations, which in terms later converted into poor policy. So if you have enough sample manually, you can learn it. If you have a very huge amount of input data you have, then you can't ask an expert for manually labeling every sample. That is too a not very optimal solution. So what you do, you try to learn from the data. That is what they did. So they proposed a confidence aware framework where they can handle mixed quality demonstrations. And once they try to find out which of the demonstration are very suboptimal, they just prioritize the optimal ones, and then they try to learn the policy with the better policy with the demonstration. So what they did is suboptimal, every time they learn that this demonstration is not good, they de-weight it and just make its weight less on the model. And now you have a model trained on more on the demonstration which you are more confident about. So how they did it? So at first, for each demonstration, the whole set of demonstration, they randomly assigned some like 0.5 or 0 to 1, which is like 0.5 as the confidence on each sample. Then they try to do a bi-level optimization problem. They try to solve a bi-level optimization problem, which is inner loop is kind of similar to accuracy in a you have some accuracy. You are training your model based on accuracy. The more accuracy you are getting, the more better model is. Still you don't know that the for which demonstration are optimal or not optimal. You have to still confidence on the get the confidence of the each demonstration. So for that optimization, they enabled another outer loop, which is they labeled a few examples with expert, and if the some decision is very far from that example set of decision, they calculate another error and repropagate it to the model. So what happened is now your model, and when they propagate it to the model automatically adjusts for which samples I'm going too far from that set of sample demonstrations, and they decrease the gradient wise, they decrease the weight of that samples, those making the model going too far from the optimal samples they have listed as a smaller kernel samples. Now what happened is when they train enough time, the samples that are making the model going far from the optimal set of samples, automatically their confidence score decreases, and they throughout the time they have very little impact on the model. So they claim this can be applied to robotics control, where you want to learn from both expert and novice together, and you as novice doesn't have as expert opinion, you have little impact on the model, so there you can take. Or you have driving logs where unreliable driving behavior are happen, so you automatically devalue the driving behavior that is not up to the mark. And any more domain where there is a risk of suboptimal samples. So another popular approach for handling out of distribution sample is dagger or multi-step prediction. So what happens is dagger is like you train the model makes some decision and make some mistake, like you are trained it that robot to make coffee and uh, it spilled the coffee or the milk something. Now the model asks an expert says that and label it like if it for this input data it makes this decision, it have to make that, it doesn't do that. And they like track it, and then for the next policy update they retrain with the new that expert decision. But there is like 2015 a AAA AI paper came out, data as a demonstrator. They tried to remove the expert from it. They try to automatically adjust the model. So what that is like they try to do is like the model makes a mistake and they try to put the error within the new sample automatically, and that they compare that trajectory with the best sample, and they try to get the optimal error and put it in the training data, and automatically they learn it. So I covered that paper here. So this is the data as demonstration, the publication actually. It was published in 2015 AAAI. It was part of a thesis. So there are some more papers. So they kind of they consider the whole behavior cloning paper as thing as a sequential decision making or stuff. So what happened is in sequential decision making, you are predicting some trajectory. So once you make a decision, it is putting as input for the next decision. So if you make slight error on current decision, what happens is the trajectory automatically changes. So every time you make error on one decision, and automatically this decision accumulated for the next decision, and over the time you get a completely different trajectory, which might not be even very different than what happened in the data set. And this error actually gets you to the very noisy output. So to this distribution mismatch actually so based on, because this distribution mismatch happened based on the model's own decision, own error. So that is what they tried to actually address in this, and they didn't try to involve expert with it. They tried to do it automatically from the data. So what they did they actually model to handle its own mistake by exposing it during the training. So what happened is when a model is trained, they roll out the trajectories. Like the rolling out means you make a decision, they add that decision to a new trajectory. Using that decision, they create a new trajectory, and then they compare that new trajectory based decision with the ground truth states. There are some counter states they carry. They compare them, and then they correct the error. What should be the decision, and that they feed it into the as an input. Now you have a larger set of data, input data, and when you retrain it, you have like completely another policy based on your output, modified outputs. So this way, when you train again and again and again, your data set also enriches and you have better. But I was actually going through trying to implement this paper. Then I found out that problem is like these trajectories are not exploring very highly. They are kind of even within the distribution. If you have some sample, slight changes trajectory almost keeps it within the same distribution scale. Doesn't cover very out of a distribution which not in the very much different than the distribution samples. So another is I want to cover is like inverse reinforcement learning for behavioral coding. Uh, Inverse reinforcement learning can be like model based or model free. In model based, you have some kind of rules or simulator. You know that what environment will make decision based on some states, and based on that, you try to somehow extract a reward based on the data you have and the model. But sometimes model phrase you don't even have that. You have some only expert demonstrations. You only know that experts some made decisions, and you want to infer the reward from that. So this is the one paper I want to cover, that is Bayesian inverse reinforcement learning. It actually it published in 2013, and it is a medical based paper which try to mimic the diabetes treatment of clinician decision. They are actually kind of, their novelty is not high. They like diabetes treatment is itself a clinical decisions, sequential decisions, and there is no explicit reward. Why doctor give that medication for some patient? So they try to get that intention. So what they did is they did the straightforward implementation of another paper, that is inverse reinforcement, Bayesian inverse reinforcement learning paper, which was published by Ramachandran and Ahmed during 2007. They use Bayesian statistics to compute the reward function, and they directly applied it for that decision making process of uh, what we can say diabetes patients, where doctor made diabetes decisions, certain decisions for diabetes patients. So what they did it, so I covered the main mechanism of the inverse reinforcement learning. So in case of inverse reinforcement learning, you have the states, you have kind of an environment, you have a certain model actually here, you have some here, know the environment, what states it has, what action I want to take, and other stuff and everything, a typical MDP environment, and you try to pick a reward function. You try to find a reward, you guess the reward. So initially what you do is, for the reward function, and you assume that a random reward, and you also assume that this reward will follow certain function. For example, it follows Gaussian function. It will have a mean and distribution. If you somehow learn the mean, you know that the main reward will be around that mean. So it can be, if based on the environment type, it can be any other function like Laplacian, uniform, linear, whatever you say. So what that does it, like they know that, for example, you have like 100 states, 1,000 states. They consider a 1,000 state vector. For each state, there is a reward. They initially assume that is a reward vector. And the reward function, what does it? It tries to, if you are using Gaussian function, it tries to learn the distribution of that Gaussian reward function. Okay. And what confidence it has? It has only the expert evidences, like the decision from the experts, data. So first, what they like try to say, like initially you guess the random reward if based on your actions. You have 1,000 states, and for 1,000 states, you have, for every state you have some reward. If we revisit my let's say this one, say like it has 3 state, and these are the reward we are mapping for each action, and these are the reward, let's assume, for each action. So maximum reward is 0.9. So you are assuming the maximum reward. Actually, try kind of. Let me go to the, okay. Now what happened is, like initially you assume that that is the reward, but obviously that is not. You are trying to know that the policy which will get the best reward under for the data. Then for that reward, you try to assume, actually, if I assume this is the reward, which action actually I'm going to make. So you actually try to map the reward to the policy, which is Q. Then also you put in some uncertainty with some like temperature alpha. So uncertainty is like something like that is like, you say like, even if your expert doesn't make consistent decision, even you know that you have certain reward, it always won't select the optimal decision. It's for softmax, it will with certain probability it will explore among the suboptimal. But you, over the time, based on the reward, you calculate what is the probability of the different action with the optimal action, or if you with minor exploration some action. And from that you like calculate the log likelihood of the actions, like based on the reward, let's assume we are only getting the optimal actions. What is the log likelihood of our actions? And we get the total log likelihood of our different actions. Now we can, once we get the under this reward, what is the likelihood of the actions, and we have the actually, now this, actually this log likelihood is not the reward, not the maximum, sorry, it is the likelihood of the expert actions. So under this reward, what is the likelihood of the expert action? Now if the reward you assumed initially is very far from the expert's reward, what will happen is the likelihood you will get is very low. So your objective will be like increasing that reward, like increasing that likelihood. So you would take like a Bayesian, you have like now prior reward, you now assume that the new, what should be the new likelihood. So you just use the Bayesian update, and you get new posterior. Then next you use that again, and next from that posterior you just again somehow a mean map, or somehow you use some function to get new set of reward. And again you try to see that if this new set of reward matches the expert decision, unless this reward get very close to the expert decision. By the time you learn that reward function, you already learned the like intention of the your model already kind of modeling the expert intention, and then you use that reward to get the like optimal policy. So actually till now this is what I covered. Now if we compare behavioral cloning with IRL, these two prominent one, we can see that behavioral cloning is very simple. You just train a model, and it is only effective if your expert decision consistent and has very high quality, and covers very large area of data. But cons are, if you have a small data set, it's not good, and it doesn't explore, so there is no chance of exploration, and an out of distribution situation or unseen situation, it will fail surely. In inverse reinforcement learning, you are trying to actually learning the intention or reward function, which can be improved. And optimally what will happen once you based learn the intention of the or reward of the certain action, you just try to make the actions that satisfied that function. So you have like more flexibility, and you can say like why your model making certain decisions, because you know the intention function. But problem is like this is the Bayesian one, which is like more simpler one I covered. But actually truly the learning the function is more harder, because like for example I'm assuming the Gaussian function, but the intention can be very chaotic. The like a clinician can make chaotic decisions and very chaotic situations. So if your function is extremely nonlinear, how do you make that like map it? So there are actually, I have seen people are using like generative models, or currently using nonlinear, as reward can be very nonlinear. They are trying to use like using generative models or something to learn that reward function, because they don't know like which function will able to cover that reward. So that is another problem. So actually, till now, this is what I want to cover till now. Do you have any questions or anything for me?
Yeah, from audience, if anyone have any question, you can came to near to mic and you can ask. Your mic is off. Right. Zia, can you turn on mic here?
No. Hello, am I audible?
Yeah, you can
Yeah.
ask.
Yeah, thank you, Professor, for the talk. Actually, I have a question regarding the inverse reinforcement learning. As you
Mhm.
told us that here we try to infer the expert's motivation or expert's intention, like
Mhm.
not like can the expert tell us directly like what's their intention rather than we trying to find it.
Yeah.
That makes sense.
So can you repeat?
Yeah. So rather than like intention learning, trying to find the intention, like is it like possible, for example, a doctor or an expert poker player tell their motivation, like they are trying to do this.
Yeah, that is the main idea. Main idea is when so based on the data or environment you have, they try to see like if we can map the action making process into some function. So that is the main idea. If we can some convert it intention to function, so you can mathematically explain that why certain decision is made. So once certain you more convert it into some function, you can always like function can be considered different ways. Function you can explore the functions space and everything. This way you can explore the different decision making process too. But the idea of inverse reinforcement learning is like fast converting data into the function. So to be honest, everything is kind of when we are even learning the supervised learning and everything using data, we are trying to actually kind of converting the data into the function. The model is also a function. That is another kind of function, but there we are trying to learn the intention.
Yeah, thank you. I also have another question. For example, there is
Yeah.
a situation, right, where there are multiple valid actions. For example, in a self-driving car, like there is an obstacle
Mhm.
ahead of us, like so we can take left, also a right. So for a situation where there
Mhm.
can be multiple valid action, how imitation learning deal with it?
So basically, if you have multiple validation and it's ultimately the end of the day, it's getting the like which one gives it best reward. If goes to the basic reinforcement learning, if you have two action which making the same amount of reward, then you are randomly choose one, right?
Yeah.
But throughout the time, once over the time, the policy one reward will be optimal. It is very rarely that after a large amount of time you will always have to action always giving you the same reward. Imitation learning is also the similar. It's not very far from that concept of reinforcement learning. It is also learning the policy. Ultimately, which one gives it the best reward, it will always stick to that.
Thank you.
So just only one difference is like in reinforcement learning we have direct the reward function, but imitation learning we don't have directly reward function. Behavioral cloning is assuming reward is hidden within the data, but in inverse reinforcement learning we are getting the reward. Once you get the reward, you can always update your model. So there is a one thing. Sometimes people initially start with the basic behavioral cloning model where they have the model but no reward. Then uses that model sometimes to get a reward function. Now they know that how why model is behaving that way. Then that they can use the reward function. They can go for some simulation function because now they have some reward function, they can simulate and update it. So you can think it like it can be a stepwise process. You when you have some data, nothing else, you can start with a basic model, then go for a reward model, then go for a like a pure RL model. But for pure RL model, you need something. And imitation learning has a lower amount of sample, you don't have anything.
Can you hear me?
Yeah.
I have a question. If in imitation learning, during the learning by like teacher, if there is error, how the imitation learning to understand in the like buying imitation, like if there have some errors, how it's handle the situation.
So basically, actually, what I covered is very, to be honest, very surface level of the imitation learning. So presently, actually, if you go through it, these are the very basic imitation learning algorithms. You go through it, there are more like complex situation. Every time a complex situation, you learn the model imitate certain type of error start appearing, and it doesn't handle it well. So they work with that complex situation. Now there are different kind of steps. I covered like very basic, you can say supervised learning stuff. But now if you follow the imitation learning models, you will say that they directly went into the generative models. Now problem with the generative models, sir, they are black box. You don't know the what the hidden, like how the decision is being corrected. You know that model is kind of learning from the action. But if you go to on the very basic stuff, understand it. For example, like one particular example can be confidence based querying. I'm covered it published in 2021, but it is what very close to what you are answering. If certain decision it tracks like this decision is making me very far from the expert decision, so they try to trace it and like to decrease it confidence. So kind of what that is they're kind of enforcing their model to only consider highly the strong decisions. So still, these are very surface level, I would say, very surface level solutions. This one is, I think, one of the closest solution. But if you start exploring it, you find that actually whereas now they are developing more complex and complex ones, which are complex mathematical models. For example, I covered just Bayesian, normal Bayesian model for inverse reinforcement learning. But they actually, if they try to handle it mathematically, they go for more complex and way more complex models using generative models or any other stuff for every type of decision. So I will recommend, you can truly interested, you can search. For example, there is Bayesian inverse reinforcement learning. There is another one is I think causal reinforcement learning, inverse reinforcement learning, maximum causal inverse reinforcement learning. That completely takes another approach, which is more complicated. So it's very different.
Anyone else?
Hello, am I audible? Hello.
Yeah.
Oh, hello, Professor. So the thing is that, like, I have a doubt. While you were explaining behavioral cloning, you said two things. One thing is that it's more of supervised learning. And then you also said that it has a hidden reward like reinforcement learning. So if you could, like, give me proper comparisons because I'm still having doubts in behavior cloning.
Oh, so basically, think it like this: that in you have applied supervised learning, right?
Yes.
So once you train a model,
We have
you
labeled data.
do you like sorry?
Supervised is more of labeled data, like we don't go outside. We are in a box thinking inside the box.
Yeah, inside that. So your what happened is like your model have to make a decision which, like, you trained with all dogs picture, and suddenly you got a bird picture. Your model will make a wrong decision, right?
Yes. But it's so
Why? Because
Yeah, because it is
So
for
because
data.
so it is called, yeah, it is a stationary policy, because its policy is stationary to the dog's picture. Now, when you start getting the bird picture, what you will do? You will retain the model, right?
Yes.
Now, once you retrain the model, your policy changed, right?
Yes.
Now your model can somehow identify the bird. Now you move to one policy to another policy. Still, that is also stationary if you get another animal. So every time, so that is the main supervised learning generally stick to one policy.
It won't.
Reinforce imitation learning is like your policy change, your decision making process change. Every time you get better action, your decision making process will update it. So that is more close to the reinforcement learning, where every time environment gives something that gives you better reward, you move to that decision. So,
So how is
so basically that is, yeah.
Professor, then how is behavioral cloning different?
So behavioral cloning is the basic one of the imitation learning. It assumes that you have a model. So basically, it is not, they don't accept it as a full-fledged imitation learning model.
Okay.
You
Full-fledged.
can say like you can't directly go to the, like you have like a very small amount of data. You can't, from using very small amount of data, you can't train a proper reinforcement learning model, right?
Yes.
A,
We can.
a reinforcement learning will be the optimal, but you need a huge amount of data to learn the proper probability of the all state space, right?
Yes.
But you don't have the environment or anything. So how you go there? You need something initially, some model that can at least copy the decision making process of the expert, right?
Yes. So it should be
So
cloned.
they are the initial step which can provide you the basic steps. So that can, like when you don't have anything, you can step on that so that you can next progress to the next model.
Okay. Thank you so much, Professor.
Mhm.
Questions?
Zia want to anything? Zia.
No more question, Arif.
Okay. So thank you, students, and sir, thank you from all of
Mhm.
students.
Okay.
Yeah.
Nice to meet you guys.
Yeah. Thank you, sir.
Okay. Bye.